morning. Welcome back.
Good morning.
I know you guys have a very busy week ahead of you, so let's cover a few housekeeping issues. The first is your midterm will not be today. It will be provided on Wednesday. For one major reason.
Yay.
That major reason is fifth floor and others consider this week to be a very busy week for you with midterms and other things. And having the midterm due back Friday would kind of conflict with a lot of other things that you're doing this week. So we pushed the midterm to Wednesday, and it will be due next Monday. So you'll have the weekend. So you have the week to focus on your other midterms. That gives you the weekend for some of you procrastinators to go ahead and complete the take-home midterm over the weekend. All right. That's the first order of business. The second order of business, I've received some questions regarding the group project. The assignment that you turned in for the group project is just the outline. So there's no data available yet, just the outline. So group members, your group title, which variables you think you're going to need. Question? Yes. So you have a little bit of time right now to submit that individually. So yes, I need, one of you is supposed to be your group contact, right? And so I'll be interfacing with that person more regularly, but everyone's supposed to submit the group assignment. Third order of business. Today's lecture is going to be our last lecture day, right? So it's going to be a little bit dry, but it's a very doable concept, simple concept that I need for us to get before we can do the testing of hypotheses. So that's what we're going to go through today. How can we actually test hypotheses when we're only dealing with a sample? After today, that is the following weeks, there'll be more lab sessions. So you got to make sure that you have a working copy of Jamovi, make sure that you feel comfortable maneuvering within the software so that you can keep up with each of the procedures that we're learning how to run in the next coming weeks. When we come back next Tuesday, I want you to be prepared to party a little bit because yesterday was my birthday.
Happy birthday, dear. Happy birthday to you.
Thank you very much. So, as I promised the D3 students, Krispy Kreme birthday donuts, but you know, they're like 20 miles from here. They don't deliver that far. So I really kind of gave it to them over the phone. So I got like 140 students waiting for Krispy Kreme donuts. They said, okay, so we're back and forth, back and forth, back and forth. So next week, they will deliver Krispy Kreme donuts for you guys and the D3s. So Monday for the D3s and Tuesday for you guys, all right? So next week we'll party, not this week. We've got a lot of studying to do this week. All right, let's jump into it. So today we're going to talk about not being fooled by randomness, actually taking advantage of randomness so that we can figure out whether differences that we are seeing are real or not. All right, so we finish up the housekeeping, and maybe just so I can expose you to some of the questions that are, or styles of questions that are on the midterm exam. Half the questions are sort of multiple choice, the other half has to do with Jamovi, all right? So what's the order of central tendencies from left to right for the following distribution? So if we had a distribution like this, first question you want to ask yourself, does it seem like it's symmetric, right? Symmetric around its mean. It kind of looks like it has a skew, doesn't it?
To the right.
Right? Yeah, skew to the right. So right skewed. If it's right skewed, what central tendency gets pulled towards the skew? The mean. Fantastic. The mode never changes. The definition of the mode is which score is always the highest, most frequent. Okay, so that's right here. That would be mode, not going to change. The one that gets pulled with the skew is the mean. So out here would probably be the mean, which would leave this one in the middle for the median. So this would probably be mode, median, mean. All right, second one. Which of the following advantages is recognized when you use the median as a central tendency? Would it be that all data values are used in the calculation? No, because normally you need to find the middle. Can also be obtained for qualitative data? No. What central tendency can we use for qualitative data? mode. So for example, like some of you are in scrubs, some of you are not in scrubs, that would be a qualitative variable. I mean, the number of people would be quantitative, but it's a qualitative variable, nominal. So the central tendency we would use would be mode, so we'll do it here. Maybe an actual meaningful value, no. The median can be a real value in the data set, or not a real value. Or not unduly influenced by extreme values. Yeah, that's the median. Median could care less about outliers, not influenced by them. Okay, question.
The first one, what was the answer again?
All data values are used in the calculation, only the mean.
The first.
Oh, the first question.
Yeah, sorry.
This one.
Yes.
What is the answer?
Yes, so mode is.
Going from left to right, it would be mode, then the median, and finally the mean. Right, because the mean is the only one that gets influenced by outliers. So if you're saying this skew out here is going to fool the central tendency, which one will fool? The mean. So that's probably this guy, the last one. All right, so for number 2, I would select not unduly influenced by extreme values. That's the median. And finally, true or false? Interquartile range comprises the middle 50% of a distribution. True, correct. Yeah. Okay, so if you're comfortable with those styles of questions and easier ones, you should be just fine for half of the midterm exam. Then the other half asks you to do very similar things that we've been doing with Jamovi. Okay. All right, so let's get into probability basics. So with the probability, we're trying to think about ways to quantify or characterize uncertainty, or frequencies, right? Frequencies with uncertainty. So what we're going to do is we're going to think about probability as a distribution of a list of possible outcomes with corresponding probabilities that satisfy these 3 rules. The first is that the outcomes listed must be disjoint. That means no overlap. So if we say we're going to split the group up today based on those who have scrubs versus those who have civilian clothes, there's no overlap. Theoretically, you could have both on, but we're saying no, you're going to be in one group. You can't be in more than one group. That's how we're going to define disjoint. Second rule is that each probability must be between 0 and 1. Okay? So a probability is between 0 and 1. If you multiply that by 100, you have its percentage. And finally, probabilities must total 1. So if we've accounted for all possible outcomes, if you add up the probabilities for all possible outcomes for that event space, the total should be 1. Which makes it nice and easy. So if you have one probability, let's say there are only 2 possible outcomes. If you have 1, if you just take the subtraction from 1, you get the other. Okay, so you get the complement. Let's think about a die. So a die has 6 sides, at least the one we have here has 6 sides. If it's an unweighted die, that means you could, if you roll it, you could get any one of the 6, which would give a probability for any one of the sides. What is that? What is the probability of any one of the sides if it's a 6-sided die?
1 out of 6.
1 out of 6, so somewhere near 0.167, or 1/6 with the line over it, which keeps going on forever. So if we're going to assume here on the y-axis is the true probability of getting one of those sides of the die at 0.16, the question is, will we actually get that if we only roll the die maybe 1, 2, 3, 4, 5 times and just kind of took the average? What do you think? How many rolls would it take for us to be certain that the probability for one of these sides would be 0.167? Oh, I hear 1,000, 100. Oh, I'm hearing as it increases, we get closer, and that is what the law of large numbers tells us. Is that when you are dealing with small sample sizes, the probability estimates that you get vary wildly. But once you're dealing with larger sample sizes, and it's kind of interesting because here, after you get to about 30 or so, it starts to settle down. After you get between 1,000 and 10,000, it really starts to settle down. You need large sample sizes to have really good estimates about what that probability is. Okay? So again, we might not know what the probability is, but if you try to tackle it with a larger sample size, then you have a really good idea of what the real probability is. With smaller sample sizes though, we're going to get these wild estimates that are not anywhere close to what the real probability is. Okay? So the law of large numbers says, hey, large sample sizes, you get really good estimates about what the true probability is. If you take that away from today, we're golden, all right? Law of large numbers. If we took 2 die, 6-sided, and we rolled them, the question then becomes, which observations or dice sums would be most frequent? Would it be 2, 3, 4, all the way up to 12? So again, you go 1 through 6 on one die, 1 through 6 on another die, you're rolling both of them, you're adding up the results. The question is, which is most frequent? And you can see here, which is most frequent? The 7, right? And you can see here from this histogram that the 7 is the most frequent. Will you always get a 7 when you roll the 2 die? No, you will not always get a 7. Sometimes you'll get a 2, sometimes a 5, sometimes an 11, sometimes a 12. But more often than not, you will get a 7, or a 6 or 8, or a 5 or 9, and so on, until you get this kind of pattern. And in those earlier gambling eras, this is what they used to kind of figure out, what should I bet on? Yeah. And you know how many rolls of the die it would take? Tens of thousands, hundreds of thousands. They would pay these guys to just kind of keep playing the game, keep playing the game, keep playing the game, so that they can build this map to figure out, how should I bet? Right? And that's how we understood these statistical probabilities and principles, is from early gamblers. And so now we know I should bet on a 7 or a 6 or 8, because that is what's going to likely most happen. However, it also says that I shouldn't just roll once or twice. I should play this game for about 3 weeks to make my money. Right? All right, so probability and inferential statistics. How are we going to use this probability? Well, probability is this link. We have a sample, but we're interested in the population. But we're going to use what we know about probability to kind of link our sample to that population so that we can then do what's called inference. So inferential statistics is what we're going to do now. What you've done up to this point is called descriptive statistics, simply describing what I see. But now what we're going to do is inferential statistics. We're going to infer something about the population from our sample. Okay? And the way to do that is with probability. So probability tells me you can take, if you have this population and you extract a random sample from it, that means certain observations should be frequent and other observations should not be as frequent. Just like that map for the 2 die, when you roll the 2 die. When you're able to do that and build this map, right, then you get this distribution called the standard normal distribution. And the standard normal distribution has certain properties that go along with it, which we'll discuss in a minute. But again, if you randomly sample from this population, you take all these observations in that sample and plot them, you should get something that looks like this. So last year, I tried to explain this with the classes that, coin flips, die rolls are supposed to be random processes. For those of you into sports, at the Super Bowl, there's a coin flip at the beginning of the game to determine who gets to make the choice as to whether they want to receive or kick the ball. And there was a period of time not that long ago when the NFC, they called it right for about 14 times in a row, 14 seasons in a row, they called the coin flip correctly. Now the question, if you're in Vegas or somewhere else and you're betting on the game, is should that even matter, right? Because you might think, well, if I get to choose whether I receive the ball kick first, that means I have an advantage and I'm more likely to win the game. So what we did last year is we tried to determine if you called the coin flip accurately, were you more likely to win the game? So we collected the data, we put the data into SPSS. This year you guys are working with Jamovi though. So we collected the actual Super Bowl, who the matchup was, what the coin toss outcome was, the team that was the coin toss winner, and what the game outcome was. Did they actually win the game or not? And we try to identify, the coin toss outcome, we try to identify some patterns. So oftentimes when you think about a random process, people think it constantly flips back and forth, A, B, A, B, A. That's actually not random. A truly random process actually has some natural clusters in it. So although sometimes you would say, oh wait, heads, tails. Oh, these are patterns. They might not be patterns. They might just be natural clusters, which can be part of a natural process. So So we ran a crosstabs and a procedure that you're going to learn later too, which is called a chi-square analysis. This chi-square analysis showed us that we get just about the same outcome whether they won the game or not in terms of the coin toss. And so what we find here in this column, this is called the exact significance. This is its p-value. And we see that the p-value is what?
1.
Is it greater than or less than that 0.05 threshold?
Greater.
It's greater than. In fact, when we're learning about probabilities, we said probabilities range between 0 and 1, right? This is 1. This rarely ever happens. But again, we're looking at this distribution between the coin toss, winning the coin toss, and the game outcome. Our hypothesis is, oh, if you win the coin toss, you're probably more likely to win the game. This is saying there is no relationship at all between the coin toss and the game outcome. In fact, this 1.0 says it is a completely random process. There is no relationship whatsoever. That's what a 1.0 means. A 0.05 or less than 0.05 would have meant, ooh, it looks like there is a relationship. You're more likely to win or lose the game if you win the coin toss. But this p-value, this conditional p-value, says, assuming that it's a random process, we should exactly expect what we see. A 1.0 means it happens all the time. 0.04 probability means it never happens. 1.0 means it always happens. This is saying that random process of coin flipping should always lead to the outcome we just saw in terms of game outcome. Okay, so for betting on the games, don't factor the coin toss winner or the coin toss outcome into your bet at all. All right? At least that's what this data says. Actually, I shouldn't have said that. This campus does not advocate gambling. Neither do I. Unless you actually know what you're doing, like counting cards. I didn't say that. Any of you recording?
I didn't hear that.
Yes.
All right. So the conditional probability, this is our p-value. It's not a straight probability, it's a condition, which means there's an if in there, right? An if. So the p-value says if the null hypothesis is true, what's the likelihood that you would see the results that you got? I don't expect you to remember this math here. Okay? I don't expect you to do that at all. I simply want you to understand that the conditional probability has a given. What's the probability of an event be given another event, A? So what's the probability that you would see what you've seen? Again, you're doing your research. What's the probability you would see that assuming or given that the null hypothesis is true? That's the if-then. So here's how we write it. P-value is actually the probability of obtaining the observed effect, that's what you measure in your research, or a more extreme value. So remember, when we're talking about probabilities, we have to account for all possible events. So it's not just what you observe, it's what you observed or more extreme. So that takes everything in that direction, given that the null hypothesis is true. The reason why that's so important is the null hypothesis is always a state of randomness. If randomness was responsible for what you saw, how likely would it be responsible for what you actually observed? So if what you observed is random, the two should look very similar. If what you observed is not random, the two won't look very similar at all. And that's why we accept a low probability. All right, so far we've been using the p-value to make a very dichotomous kind of decision. There is a difference or there isn't a difference, right? But I want to actually gradate that a little bit further. I want you to think about probabilities this way, or at least the p-value. If the p-value is less than 1%, so convert that 1% to a probability, what should that look like? Exactly, 0.01. So if the p-value is less than 0.01, then we're going to say that that is overwhelming evidence that supports the alternative hypothesis. Okay? And the alternative hypothesis being the description of there's a real difference here, a real effect. Okay, so p-value of 0.01, there's overwhelming evidence, 0.1 or less. P-value between 0.01 and convert 5% to a probability? 0.05, right? So if you go from 1% to 5%, then we're going to say that's strong evidence for our alternative hypothesis, right? And finally, between 5% and 10%, this is where most people say, oh, there's no difference. And this is where I want you to say, nope, don't say that there's no difference. What I'd rather you say is there's weak evidence to support the hypothesis. Not no difference, just weak evidence. And then finally, if the p-value exceeds 10%, then we can say there's no evidence in favor of the alternative hypothesis. So I really want you to understand this well, because as I was explaining to some of you, the last half of this class will really appeal to you as clinicians. So the first half, I'm kind of appealing to more of the arts. I'm asking you to observe and describe what you're observing. But in this last half, the arts is there, but we kind of put it off to the side. Now we become far more scientific. If you have a p-value of 0.01, you must describe it this way, as overwhelming evidence. If it's 1 to 5%, strong evidence. If it's 5 to 10%, weak evidence. Greater than 10%, no evidence. Okay? We're very procedural in what we want to see you describe for your outcomes and your results. And so every week, I'm adding more and more to the list of this is how you describe, this is how you describe, this is how you describe, this is how you describe. Okay? How are we doing so far? We're all caught up in terms of understanding a probability. We're all caught up in understanding that the p-value is a special kind of probability. It's a conditioned probability or conditional probability. We're good there so far? And we're understanding that based on the p-value, we're going to have overwhelming evidence, strong evidence, all the way down to no evidence. All right, if we've got that and the law of large numbers, I think we're good to move on. So when we were talking about the coin flip and sometimes even the die, the coin flip is what's called a binomial process, or has a binomial outcome. There's only two possible outcomes there, heads or tails, yes or no. We can convert a binomial process to something that looks far more continuous just by adjusting the bin size. The bin size being how many observations do we see between, let's say, here and here. So if we were rolling the die, it's going from 2, 3, 4, 5, all the way up to 12. And then for the binomial process, we still try to convert that 0 to 1 into measures in between, measures in between, measures in between. And if we can convert those to really small, tiny rectangles, we get something that looks far more continuous, where we're able to actually integrate. Sorry you have to use that term, a calculus term, but we can integrate across there and calculate area under the curve. Do you remember when we said that one of the features of probability is that all possible events should sum up to 1.0? Right, that's what we're trying to do. When you create this distribution with all these possible scores, we're going to say that the area under the curve sums to 1.0. So that means we have all the probabilities. Now, to get our p-value, what we're saying is, when we said the p-value is, what's the likelihood that you would get what you observed or something more extreme? Now what we can do is we can go into this distribution and say, right here, we're going to say, if you're right here, that's where we're going to say you're an extreme finding, that or more extreme. So we're going to drop a threshold right there. So now we can say, okay, if I come in here and I find that my observation is either right here or in this area over here, I get to reject the null hypothesis because I'm saying this is going to be, let's say, 5%. Remember the p-value of 0.05? So now I'm taking that actual area and saying, where is it in the distribution? Oh, I'm going to put 5% here. Or I can say, I'm going to put the 5% here. Or I could say, I'm going to take that 5% and I'm going to split it in half. So I'm going to say 2.5% up here or 2.5% down there. So if I find that you're either in this region here or in this region here, I'm going to reject the null hypothesis. That's how the tests work. So when you get a p-value and it says, oh, p is 0.026, what does that mean? It took your value, went into this distribution, dropped some thresholds and said, the area under the curve here, is it 2%, 5%, 10%, 11%? Where is it? So now that you understand probabilities, I'm not going to have you actually do this. I just want you to understand this is what's happening. A map is being created. They're taking your value, converting it to a probability, and sticking it in this map to find out where is it. Is it in that 5% threshold or not in that 5% threshold? As we do this every week, we'll start to get the hang of it. So let's talk a little bit more about the normal distribution and some characteristics about it. First, it's bell-shaped, not triangle-shaped, not octagon-shaped, not squiggly-shaped. It's bell-shaped, right? It's also symmetric, so there's a middle where the central tendency is, and that bell should be nice and symmetric around that middle. And finally, if it is a perfect normal distribution, and theoretically, we can always think about the perfect, the mean and the median and the mode are all the same value. Okay? So again, in a perfectly normal distribution, the mean equals the median equals the mode. That's helpful to us because that helps us to be able to navigate in that distribution very easily. Okay? When we want to move around in that normal distribution, right? If we want to go from this score, like right here is our mean. If we want to go from our mean to another score in that distribution, the number of steps you have to take to get there are called standard deviation units. Okay? So yes, you can say, I got a 95 on the midterm, and then I got a 99 on the final exam, but the difference really isn't 4 percentage points, because the midterm exam had a totally different mean and standard deviation, right, than the final exam, at least we think. So if I want to say, well, how much did my score improve or change from the midterm to the final exam, I have to find out what the standard deviation change is. Because it might be that I actually did worse. Yes?
So standard deviation change is the steps it takes to get there?
Yeah, right. So if I want to move from here to here, I can say, oh, that's 4 percentage points. But that really doesn't characterize how far I move. Because let's say, like when you're running some of the Olympics, your scores are typically thrown out, or training for the Olympics, or in the races leading up to the Olympics, your scores are thrown out if your run was wind aided, right? If it was wind aided, you got help. It was natural help. You couldn't help it, but it was help. And that means it was too easy for you to cover that ground. The same thing here. When you move from here to here, in some schools it might be easy. In other schools it might be harder. So if the standard deviation for that distribution is really tiny, it's harder to move. Right? So a 95 here, let's say you got a 90, let's say the mean was a 95 and you got a 97. But the standard deviation here, if the standard deviation is like 1 or 2 points, 97 looks really good compared to 95. In fact, it's 2 standard deviations away, which means 97.5% of the group did worse than you, even though the mean was a 95. So it's important to get standard deviation units for movement, not just the raw score, because raw score only tells you half of what's going on. You also need to know how difficult is that. All right, do I need for you to memorize this? This is the function for the normal curve. No, no, do not memorize it. Although I'd be very impressed if you did. What I do want you to realize is what's in red. Do you see the red sigma here and the red mu? Did you already learn that in your reading, what the Greek means here? What's mu? It's the mean. Fantastic. What's sigma? Standard deviation. So all these normal curves that you see, this is how you write those normal curves. This is how you make it. So whether it's really flat or whether it becomes peaked, this is how you write it. And it's only based on mu and standard deviation, sigma. Everything else is, let's say, a constant or is a raw score. But this is how you write the function. Very easy, actually. Okay? That's all I want you to understand. A distribution, normal distribution, is based on its mean and standard deviation. Everything else is standard. You don't need to memorize that. So Sunshine, you and I were having a little discussion about moving in a distribution and calling them standard deviation units. Those standard deviation units have a special name when you're trying to move around in a distribution. They are called z-scores. Z-scores. How do I calculate a z-score? Oops, sorry. I'm jumping ahead here. This is how you calculate a z-score. I take my distribution, right? It's got a mean and standard deviation. I take any score in that distribution. If I subtract the mean and divide by the standard deviation, that process is called standardization. Have you ever heard that before? Standardize a score. This is what that means. They take the mean and standard deviation and they just subtract the score. Or flip it around. Okay, so you take your score, subtract the mean from it. That's what we all do. Then we stop. But that's not what you're supposed to do. Go further, divide by the standard deviation. Now you've standardized the score. And this z, as we were saying before, those are standard deviation units. So now you know how far away that score is from the mean in standard deviation units. Okay? So if you live in LA, partner or whatever, and you figure out you guys have to move to New York, you don't want to adjust your standard of living, that means you want to keep the same z-score. So maybe you're a 1%er now, you still want to be a 1%er when you get to New York. The question is, so how much does our salary need to change, or income need to change, in order to stay in the 1%, but now in New York, not in LA? So if you want to do that, you have to figure out, well, in LA, what's your z-score for your income? Then you say, work backwards in New York and say, what z-score is associated with being in the 1% in New York? And now you can compare the z-scores and say, ooh, or work backwards and find out what the score is. So here I have my salary here, but then in New York, when I work backwards, I find out the score here that needs to equate this z-score, this income needs to be maybe 15% more, or 20% more. Now, New York is a little bit different. Higher cost of living. But now you have an idea of how to maintain the same z-score in standard deviation units. We can only compare between distributions if you standardize the scores. Without standardizing, no comparison. Sunshine.
So for the units, can you describe what the x is?
Yeah. So the x is the actual score. So right now you're looking at z-scores. See how it's 0, 1, 2, 3, and negative 1, negative 2, negative 3. This distribution has the actual raw scores. These could be your patient scores, could be your income scores. This could be time to certain events for your clinic. These are your raw scores. To convert these raw scores to a z distribution, you have to take every single score, subtract the mean for this distribution, and then divide by the standard deviation for this distribution, then you get this new map. It looks just like this one, but all these scores now have been converted to z-scores. That's a good question. So let me back up just a little bit. Z-scores identify exact locations in a distribution. Okay? Exact locations, not just the score, the exact location of that score in the distribution. And we can use z-scores descriptively, so one, where am I in this distribution? Or we can use it as an inferential statistic, and that is, how far away is the score and is it statistically significant? That's what's so important about the z-score. It's our first statistical test. It's our first statistical test. And what it does is it builds now a map. You see in this table, there are columns and then there are rows. In this column and in the first row, these are the actual z-scores. If you're dealing with a distribution like this, every single distribution that's normally distributed like this, every single one follows this map. So it doesn't matter what you're measuring. If it looks like this map pertains to it. And what you can do is you take this z-score, so convert any score to a z-score, and inside here, the rest of the table shows you what probability is associated with that score. So in this table, it'll show you how much of the area under the curve is below that z-score. So for example, let's take the middle of the distribution. A mean should have a z-score of 0, right? Mean should have a z-score of 0. So let's go to a z-score of 0. So z of 0.0. What do you see there? What value is there?
0.5.
0.5, because half of the distribution is below the mean. Remember, for a perfectly symmetric distribution, mean is also equal to the median, and the median splits the distribution in half, right? Z-score at the mean or median splits the distribution in half.
Sure.
So every other value here tells you if you have a certain Z-score, what area under the curve is associated with that Z-score. So once you take your raw score, convert it to a Z-score, you go to this table and it'll tell you area under the curve. Question?
The probability that does not relate at all to the read evidence versus.
It does relate. So let's say, for example, you're actually testing a hypothesis. And you say, okay, I want to determine whether what I observed is strong evidence. So what do we say is the threshold for strong evidence?
0 to 1.
Right, 0.01. So now I can work backward and say, I know I want to split the distribution so that 0.01 is to the right, because that's going to have all those extreme values, and how much is to the left? No, not 0.25. So all we do is take 1.0 and subtract what we want. 1.0 minus 0.01?
0.9.
Yes, 0.9. So all I have to do is come in here and say, I need to find the Z-score that gives me 0.99 to the left. I'm looking. And where do I find that? Where's 0.99? As close to 0.99 as I can get. Where is this close?
0.233.
Right here?
2.3.
2.33.
2.4? No, 2.
Yeah, so here, I'm going to a Z-score of 2.33. So if I work backwards, I can reconfigure that equation and say, what x would give me a Z-score of 2.33? See? So you go here, you say, instead of z equals x minus mu over sigma, I say sigma times z, I'm going to move this over as sigma times z, plus mu equals x. So now I can solve for x. Now I can work backward and say, I need to find a score, this specific score in this distribution to split it at 1%. That's how you find those extreme scores. So yes, it is related. I know some of you look like your minds have just been blown, and that's why we use Jamovi. Jamovi does all of this for you. It just says, bing, here's your p-value, right? You don't have to go through and do all the table nonsense and kind of find out what I need, etc., blah, blah, blah. If you want to geek out on the back of a napkin, you can. You've got the formula now. But if you want to use Jamovi, you can use Jamovi too. Right? You with me so far? I mean, are you getting the idea that something really cool and funky is happening under the hood, and that's how we're getting these p-values? Yeah, okay. All right. When we do that, now you just saw the table. Now let's look at the map. The map says this. These are now z-scores. Our mean is right in the middle at 0. If I ever want to kind of figure out what proportion or area under the curve is associated with the score, I can use this map. And this is why they say, look, if you can split a distribution up between one standard deviation, so one standard deviation above, one standard deviation below, add those up. What's this area under the curve plus this area under the curve? Approximately. Approximately 0.7, right, approximately 0.7, more specifically, closer to 68%. That's why they say 68% of the distribution is within one standard deviation, if it's a normal standard deviation, normal distribution. And how much is within 2 standard deviations? Say if you go through and you say, okay, we're going to take this, plus this, plus this, plus this. What's that? 95%. So if you added up all these 4 segments here, you get approximately 95%, which means, again, within 2 standard deviations of the mean is 95% of the distribution. You can go out even further. This is going back to Lucille. What Lucille is saying, if you go back to, let's say, 3 standard deviations, now I add this, plus this, plus this, and this, plus this, plus this. That takes me to these flags of 3. If I add up all of those, I get closer to 99 or 99.7% of the distribution. Okay, so if you can keep in your mind 1 standard deviation, 68%, 2 standard deviations, 95%, 3 standard deviations, 99.7%. Now you have an idea of how the distribution is split up based on those flag posts. So 1 standard deviation, 68% within, which means how much is outside? A lot? Just 1 minus,
32%.
yeah, 100% minus 68%, approximately 32% is outside. If I say 2 standard deviations, inside of that is 95%, which means how much is outside? 5%. Bingo, that's how we're testing these hypotheses. Where 5% is outside, which is called extreme, and 95% is within. So that's why we say if you're 5%, or if you're less than 0.05, that means you're in the extreme portions of this distribution. And 95% is within.
So the extreme is the less.
The extreme is the less. Extreme is what's outside in the tail. So the question is, how big or small do you want these tails? You get to decide. Do you want 32% outside? Do you want 5% outside? Do you want less than 1% outside? It's up to you how extreme you want the data to be before you say, that wasn't due to a normal process or a random process. All right, I saw a couple questions. I want to take those before we take a break. I saw some hands. Yes.
Is there a standard for what we make, for research, for what we make our confidence interval or alpha?
Is there a standard for what we should choose as that cutoff threshold? Yes, and that's the 5%. 2 standard deviations. We want 95% within, 5% outside. That's the standard.
So have you ever see an article, something saying with the alpha of p-value of 0.10?
Now, p-value of 0.10, in this class, we're going to say that's not junk evidence. We're just going to call that, does anyone remember from that slide? Weak evidence. So it's not no evidence, we'll just say it's weak evidence. A p-value of 0.1. P-value of 0.01 is even more rigorous than the 0.05. You know, that's even more extreme. Even less likely to be due to chance. So now that we understand that, we can get an idea of what people are trying to sell us. Other questions? I saw other hands.
Ask, because we all probably have the questions.
Yeah, no, I'm not, I don't judge you guys. We've all been there. I was on that side once. I think they're all intelligent questions. It's mine, you're trying to capture this. You all see it from different angles. Ask your question. I think it's valid. And you're right. Someone else probably has that same question. So who's brave? Some of you calling yourselves gladiators. You haven't asked any questions yet.
Can you just repeat that whole thing again, one more time?
Sure, from the beginning, if you guys have another hour. Lucille.
So, this question is maybe a lot, but I understand that some of it is like from a different person's perspective, you kind of see something else, but how do you get tested on this thing?
Right, so I'm not going to test you on the tables. I used to. So I did an extensive review of what the students were saying and the comments I was receiving in class and the scores and the kinds of questions that the students were getting right and the kinds that they were, half the distribution was getting it right, the other half not. And before what I was doing, I would have you actually read these tables and actually find these areas under the curve. Just do all of that. And half were getting that, half weren't. And so now what I'm doing is we are having a discussion about it. I want you to be aware of it. So when I ask you to, hey, here's a table, find the z-score, no. But what I will ask you to do is interpret what the p-value is from a printout. So if you do something in Jamovi, gives you a p-value, you need to understand what that p-value means. But I want you to be thinking, oh, I know in that table it's probably saying it's an extreme value, and this is probably the exact z-score. Yeah, that I will test you on. But will I test you on this map? No. Will I test you on the table? No. But will I test you on this? Oh yeah, I think you should memorize this. Will I test you on the algebra for this? Oh yes. I think algebra is a requirement for this course. If I ask you to solve for x, I expect you to be able to take standard deviation, multiply by both sides, right? So you get rid of it over here. And then move, by addition, move the mu over here, and just be left with x. Yes, I expect you to know how to do that. Yeah.
I was gonna do example problems to
Yes, with
Kinda
Jamovi.
refresh.
Yep, with Jamovi. Right now, like I said, this is fairly dry because it's just going to be lecture.
Yeah.
Okay, but next week, yes, next week after you turn in the midterm exam, we actually start doing more of this, hands-on. Yes.
Way that you could like have to probably written on board with that so that we can just rather go on.
Yeah. Yes, next week, but not today. Today is dry lecture. Got to do it. Just got to get through it. And then next week, like, yeah, I remember you said those very same words last week, but now we're doing it on the board. Okay, I remember. But I can't do that today because I think I will thoroughly confuse you. Today, just want you to hear the words, see some of the associations, let it sink in, marinate for a bit, and then next week we'll get into it on the board and with your movie. Another question? Yes?
I want to know p-value. Can you talk about p-value one more time?
Yeah, so the p-value is a special kind of probability. It's not a straight probability where we might say, what's the proportion of people here who have scrubs on? Maybe like 30%. That's not what the p-value is. P-value would be more like, what's the proportion? What is the likelihood that people have scrubs on if they have clinic duties today? That if is a clause, that if is a condition. That's like the p-value. Excuse me. So the p-value says, what's the likelihood that you would observe what you observed if the null hypothesis were true? So, for example, maybe this will resonate for some of you. Some of you believe in God, some of you don't. But for some people who do believe in God, they might say, everything happens for a reason. So you might say, what's the likelihood that something really good happened to you? They might say, oh, well, it's a miracle. God must have been the reason for it. Others might say, oh, I don't believe in God. It was just random luck that something like that happened. So the if you believe that God exists, means that you're going to ascribe a different kind of meaning to what you observe. It doesn't change what you observe, right? It's just, what's the likelihood that if I believe that there's a God, that this would happen? Oh, it's very likely, because I think that's the way he interacts with people. But for people who say, I don't believe in a God, then that means, ooh, I think that the likelihood that this is random is very, very high.
So if from that phrase, the p-value is the hypothesis if the God.
Yeah. Assuming God exists, what's the likelihood that this would happen to you? Some people will say, well, I believe that there's a God. I think it's highly likely this happened. The reason why, I don't know. It could be being taught a lesson, or I'm being given a blessing, or for those who say, assuming that I don't believe that there's a God, what's the likelihood that this would happen? Yeah. Very rare, because it's I don't believe that these kinds of things should happen. I think that's worked in the past in helping some people understand the if-then. Might help some of you, might not help some of you.
Wait, can you talk about one more time
Sure.
the p-value with the z-score?
The p-value with the z-score? Yeah. So the z-score says, here's how you navigate within the distribution. The p-value says, I will tell you the probability. For example, look at this distribution. This distribution is the null hypothesis distribution. Null hypothesis has its own meaning. This is the null hypothesis distribution. So now what you're saying is, hey, I ran a study. This is what I observed for my score or my mean. Tell me where I'm at in the null hypothesis distribution. The closer you are to this mean in the null hypothesis distribution, the more likely you should say, oh, this is not random. This is random chance. So do you remember the p-value associated with being right here at the mean? Or not the p-value, but the area under the curve associated with it? 0.5. Right. So according to our threshold of 0.05, would you reject or fail to reject the null hypothesis? You would fail to reject it. You would keep it because the area under the curve associated with that score is 0.5. If you were out here beyond the 95%, if you were out here in this yellow area, how much area under the curve is in this yellow area?
1.
1.3%.
2.5, right? Because this yellow plus that yellow is 5%. This is symmetric, so it's half. This is 2.5%. So the p-value associated with being out here would be 0.025 or less in the null hypothesis distribution. So what we're saying is, here's what I observed. Put it in the null hypothesis distribution. So x, this is what I observed. Put it in the null hypothesis distribution, which has its own mean and standard deviation, and tell me what z-score is associated with that. When I do that, if I get a z-score that's out here like 1.96 or 2 or greater, that means I'm rejecting the null hypothesis because this is extreme. There's no way that you could be from this distribution if you're up here. It's like in my undergrad, every year for 4 years, I was registered in the Asian Student Association. The reason why is because of my name. When no one saw me, even though they saw me after my freshman year, they still registered me because they would make the decision based on name only. So my roommates first year, Calvin Chen, Zuka Lin, then they would see Udo Oyoyo and say, oh, well, he's probably Asian. So they would register me in the Asian Student Association until I would show up at the first meeting, and then it's like, why are you here? You invited me. What are you talking about? Well, that's because, again, the likelihood that I came from the Asian student population is very low once they saw me. Well, when they see my meanest and deviation, my first name and last name, say, oh, you must be from here. But then when I actually showed up, it's like, no, you're
Definitely not. From
unless there's a really interesting story here. Why are you here?
Did you
So,
end up staying at the association?
sorry?
Did you end
At
up,
the dorm?
did you stay?
No. Just my roommates. My roommates they would go through and they look at the names on the door, and based on your name, they would kind of register you. So when I got to my freshman year, they saw my name, so they just registered me. So my friends and I thought it would be a kick if I showed up at the first meeting, and then I politely excused myself. I didn't want to be that much of a distraction. But it happened every year. So.
Every year you show up.
So that's what happens here is, what's the likelihood that you come from this population based on your characteristics? So if my mean and standard deviation kind of looks like I might come from this distribution, but you actually test, I show up for the test, but no, you're not from here. So that's what happens out here. Put it inside the null distribution. Does it fit? It fits if it's closer to this value. But once you pass these thresholds, you don't fit in that distribution. That's what's happening. It's going to take a while for that to sink in, but that would be my answer to your question. You bet. All right, other questions before you guys take like a 5-minute break?
Okay,
Yes.
last question.
Two questions. Two last
Oh,
questions.
Brian.
Oh, I just wanted to make sure you said that closer to the mean is more random chance?
Yeah.
Okay.
The closer you are to here, the more likely it is that you come from this distribution. The closer you are to this threshold here, this threshold, or even beyond it, that means the more likely you did not come from this distribution. Because everything now that we say has to have a probability associated with it. That's why it's so important to understand probability. No more just flat statements. You got to tack on a probability to it.
Okay.
All right, cool. Your
So,
question.
is there any way to get, like, I know some of our slides have a couple definitions, but can we get maybe like a list of definitions of all the words that we're using, null hypothesis, standard deviation we're starting to get, but there's like more
That
words.
would be a fun exercise for you and some students to work on.
I knew
And I'd be
that.
more than happy.
I knew that was
If you
coming.
guys came to my lab and wanted to ask questions, and I'm more than happy to do that. But
Okay.
will I come up with a list? No, I won't come up with
Okay.
a list because I think it would be a good exercise.
What about coming up with words, just specific words that you're like, you need to know these words, you need to understand?
I'll try and do that as we go through class
Okay,
and emphasize and say, yeah, this is really important.
and we just need to jot it.
Yeah.
Okay.
And if you feel like, no, that's not working, I really want to sit down with you, again,
Okay.
schedule time and I'll sit down and we'll, but what you asked for is a really good exercise. I like it. I don't know. Extra credit in the sense, it might help you on the midterm and final exam, or maybe less on the midterm, more on the final. Yeah.
Okay.
But I don't really, as you'll see on the quiz, I don't really ask definitional kinds of questions.
Well, just so we can understand, like
Yeah.
the way you talk, it probably seems so simple, but for us, like, wait, say that word right.
Right, exactly.
We're still trying to
Right,
understand.
it's a new language.
Yeah.
Got it.
Thank you.
You bet, thank you. All right, 5-minute break, grab some water, stretch your legs, and then let's come back and finish up.
I felt really bad later. I was like,
Because you're good at that.
I'll grab it. Always because
If there's a skew.
breast cancer, but no sarcoma. Write that down, she's getting the most checked. Oh, that is for right. Okay, yeah. Yeah, that was probably not fully formed or something. I heard the lead. I think, yeah, she's like,
Because of me,
oh, I get it.
it's fun in here.
Well, that's what I thought for another patient.
Oh, okay.
We just did this year, and when they told me about it, we had so much confidence in her. Well, like, it was like a little bit of something and some syrup. She's the best. And she got qualified. But like, there was no confidence. Well, that you could see. But on the radiography, you could see.
But I don't have my ID. Can you send her a picture ready?
You can send it, but I did that yesterday, Megan.
Yes?
I don't know what I'm doing.
It doesn't matter how far you guys are now, how far you guys are.
Whatever level they go.
And now I'm going to talk to therapist.
No, like further back. So I was just trying to do my roommates, they're all busy. One of them works
Because it's the most frequent.
Hello, Miss SOVP.
And it's chocolate.
I need to figure out.
Yeah, if you're measuring something else besides the try to illustrate what combination.
All we need to figure out is
Well, yeah, what you gotta do for the guy, you know where he gets that price. So you get a 1.
Just kidding.
But they're like bigger than that.
So this is 1 plus 1 is 2.
You can get them anywhere, Walmart, Stater Brothers, no,
Oh, because they're regular.
I like know exactly what it looks like. I'm pretty sure Stater Brothers has them, and I don't know Walmart does. Target probably does too. I know what they look like. What about like the topping? So we just have to bring it, we just have to bring it over. Oh, okay. So I just need to find out how many people.
So this would be, what's the
What do
probability?
you mean?
What we observe.
But I mean, it would be. Why? Do people want it?
No.
Oh,
You might
oh.
say, what's the probability that?
Oh, there's apple cavities
So it's, what's the likelihood?
Oh, yeah. Wait, can you see it? Oh, okay.
No, give them what you just said. That's, you were saying it?
Oh, yeah.
Give them all the what's the Yes, we convert it to numbers. Yeah, so the null hypothesis is this.
Oh, like, okay, no. So the person there, as hypothesis, maybe just like, just guessing hypothesis scenario.
Right. So assuming, so this is the null hypothesis, and it has a which you'll use. We say, assuming that this is responsible for everything that happens, what's the likelihood that this would have produced a result? You would say, not very likely.
Whenever it's close to the blue line, and it's not what,
It's weird because your hypothesis is more testable. What's this one? Not a you gotta wait a week. Yes, it's very good. Because that's how you The null can't be true if what I observe can't be responsible for
I was saying, she put up slide.
It'll come in.
I think she likes doing
You need to
All right.
Well, it's like, we're not even
Excuse me, sir, can you
Let's take
please
a
take your
look
seat?
at a quick little example of how one might use the Z-score distribution. So this is a study that was published a while ago. Its title is Time and Cost Analysis, Pediatric Dental Rehab with General Anesthesia in the Office and the Hospital Setting. So let's take a look at the first few sentences, get an idea of what this study is about. So pediatric dental patients who cannot receive dental care in the clinic due to uncooperative behavior are often referred to receive dental care under general anesthesia. At Stony Brook Medicine, dental patients requiring treatment with GA receive dental care in our outpatient facility at the Stony Brook School of Dental Medicine or the Stony Brook University Hospital ambulatory setting. This study investigates the time and cost for ambulatory American Society of Anesthesiologists Class 1 pediatric patients receiving full mouth dental rehab and GA in these two locations. Right? If you look at the part that we actually have boxed, these are the results. The average total time, that's anesthesia end time minus the anesthesia start time, to treat a child at one of these locations under GA was what?
222?
222 what?
Plus or minus.
Plus or minus.
222 minutes plus or minus 62.7. That's something you can use, right? Central tendency and dispersion? All right, so let's say that you took these numbers and you said, you know what? Over here at Loma Linda, maybe our average is about 209 minutes. I wonder where our 209 minutes would be in that distribution. Would it be considered to be an outlier, extreme? Say, oh wow, we're really different from Stony Brook. Or no, actually you're quite similar to Stony Brook. So for example, is 209 similar to 222?
Yeah. Some
Some are saying yes, right? Especially if you're looking at 62.7 minutes being a standard deviation. So here's what we'll do. We're going to, in our mind, create this map where we know that the z-score of 222 minutes is here, anchored here at the middle for the mean. And the area under the curve is sum to 1, but we know that one standard deviation will be 62.7 minutes. Okay? So what we need to do is take our formula, the x minus mu divided by sigma. What will x be? Our 209, right. What will mu be? 222. What will the standard deviation be? 62.7. All that came from the paper, right? We're just trying to figure out where's 209 in there. So 209 minus 222 divided by the 62.7. This process is called what? Standardization. So we're standardizing that score. And what do we get? We get a negative 13 divided by 62.7. If we carry that out further, our calculation should be something similar to a minus 0.207. So this z-score of minus 0.207, where is that in here? What value is it close to? Which of these z-scores is it close to?
From negative 1
Have to
to
look at that paper?
Sorry?
Don't you look at it from the other paper?
No, we're not going to look at it from the paper. We're going to look at it in the map because we now took what we needed from the paper. We took the mean and standard deviation, right? We took the mean and standard deviation from the paper. We put our score in there, our 209 from Loma Linda, and now we're going to figure out where is Loma Linda compared to this distribution, the Stony Brook distribution? So now what we're trying to do is we're trying to figure out where is a z-score of minus 0.207 in this map. Where is it on this map? It's between the -1 and 0, right? Closer to the -1 or closer to the 0?
Close to the -1.
Closer to 0.
It's closer to the 0, right? 0.2 is closer to 0 than it is to 1, right? So this -0.207 is going to be closer to the 0 than the -1. So we're saying that Loma Linda's results aren't that much different from Stony Brook. But in terms of standard deviation units, it's 0.2 of a standard deviation unit. It's not even a full standard deviation. And it's closer to 0. So now we have an idea with a standardized score of how close Loma Linda is to the Stony Brook data, which is what you can do. Just take the mean and standard deviation, take the score that you're interested in, put it in that mean and standard deviation, then you get an idea of where it is at. We would have had to have been way out here. We would have to get a z-score of 2 or greater, or -2 or more extreme, for us to say, ooh, Loma Linda's data is significantly different from the Stony Brook data. But because we're closer to the 0, we know that no, we're not all that different. But we can't make that distinction just from the 209 versus the 222. We standardize the score first, then we make our decision as to how close we are. Does that make sense? Okay, so those are two things I just want you to come away with today. Law of large numbers, right? Which means the greater your sample size, the better your estimates will be in terms of probability. The second thing, you can't just compare means anymore. You must standardize the scores in order to make comparisons. So you have to adjust by the standard deviation. Now I can compare to get an idea of how close or how far away our scores from each other. All right? Any questions? No questions. All right, so we take that 0.027, we stick it in our table. I'm not going to ask you to do that, but just because you understand now what we're doing, we get an area under the curve of 0.6064. What does that mean? We convert that 0.2 to, or that 0.27 to, or 0.207, no, it's 0.27, to a probability. This 0.6064, what does that mean?
It's within the 60%.
To the right of Z.
To the left of Z.
Right, so in this table, it's showing us everything to the left. But because it's an identity matrix or an identity table, we can also flip it and go the other direction. So since we're dealing with a negative number, we're actually not going to get a probability associated with this distribution. We actually get the inverse. So we flip it around, and now we get 60% is above that score. So 60% of the scores in the Stony Brook data are above our score, or have GA times of greater than what Loma Linda has, which isn't, it's not all that different. 50%, 60%, not all that different. All right, let's wrap up with a few questions regarding z-scores. See how, so we're all on the same page. Question?
How did you get that 0.6064 number that you got?
Yeah, so we're going to take this guy, the 0.207. Right? It should be, when you can round it to 0.21. Here, it's 0.27. It'd be better if you actually use the 0.21. Right? Yeah? Everyone with me? Be better to use the 0.21 instead of the 0.27? Yeah. So here if we use the 0.21, we get what?
Point.
58%? Is that?
Yeah.
Versus the 60% we're using before. Okay, but if you use the 0.21, which is what we calculated, z-score of 0.21, we get 58%. So that's 58% above that score that we calculated. Question?
Let me see if this works here.
Yeah. Sure. So our goal is to figure out area under the curve. This shaded area, we want to calculate that shaded area. We can get that shaded area if we figure out this score, because this score lets us navigate in that table. So we got to calculate this first. So we calculated this by doing x minus mu over sigma, and we calculated a 0.21, or 0.207, 0.21. We do that, forget that, move that over. 0.21 tells us we're at 58.32, or 0.5832, which is 58%. And it's telling us 58% is not below that z-score because it's negative, so we actually have to invert it. It's 58% is above that score. So it's not this z-score here, we have to go to the other side of the zero, then we shade everything over to the right. Okay? They don't want to reprint another version of this table, but doing the negative, so they're hoping that we would just know that we can just invert it, right? Yeah, so they don't, yeah, it would be redundant to kind of just print the opposite, so we can flip it, yes.
So that means that the p-value is strong, right?
If this were a test, right, if this were a test, this would suggest, that since we're close to the null value of Stony Brook, this would suggest that we're not different from Stony Brook, that the p-value is greater than 0.05, and that area under the curve, or at least if we were to put ourselves here, we would say we're within 95%.
Okay, because I was looking at this.
Yeah.
Is it?
So the p-value there would be where do we have more extreme scores, and that's what the shaded portion gives us. So the shaded portion says where you're at right now is 58%. 1 minus 58% would be what?
Negative 57.
42. So the p-value there would be 40.42, which is greater than 0.05. So we would say we are not significantly different from Stony Brook's numbers. No evidence, because it's greater than 0.1. Isn't that we gave 0.1? 0.4 is greater than 0.1.
Okay.
Yeah. So we would say no evidence. No evidence that Loma Linda's data is significantly different from Stony Brook's data.
Okay. So the p-value weak, or no evidence?
No evidence.
Okay.
There's no evidence that Loma Linda's data is anything different from Stony Brook's data.
Okay.
209 looks like it's different from 222, but when you standardize it,
Yeah.
it doesn't look like it's different. I see a question being generated right behind you. Yes, go ahead.
So I wrote down in my notes that 60% of the Stony Brook data is greater than the Loma Linda data. Because I thought I heard you say, is that still true?
Yeah. We're rounding. So are we going to make a big distinction between, unless we have millions resting on it, or thousands of patients, even hundreds of patients, we're not going to make a big difference between 58% and 60%.
But that's true. It's true that from this number you can figure out that the 60% of their data. So I'm trying
Absolutely.
to figure out
Yep.
what that really means.
Because this is let's go back to it. This is, let's say this is Stony Brook's data. This is their distribution. Here's their mean, and their mean was at 222. And then we found that ours is at 209, and we converted it to a z-score. So here we are at negative 0.2. So if we did that and shaded everything to the right, that would be between 58 and 60%. So we'd say 58 to 60% of Stony Brook's GA data has longer times than Loma Linda's value of 209. You can do that. So if you're an accrediting body, and you might generate a lot of data from different schools, you could build a distribution like this with a mean and standard deviation. And now when schools would kind of submit data, you could say where they were in this distribution. Are they close to the mean value, or are they starting to push out to areas that suggest, ooh, you're really different from where everyone else is. What's going on? Good? All right, let's answer a few more questions. First one, you have a z-score of -3. What does it mean? Is it A, that the score is below the sample mean, or that you have too few decimal places, or that the mean is 3 standard deviations below the particular score,
That one.
or that there's a mistake in your calculation?
See?
C, maybe, maybe not. If you didn't like C because of the sound of my voice, What else might you choose? A? All right, then the score is below the sample mean. So a negative means you're just below the mean. Now, if you want to see that the mean is below the score, no, because that's not what a negative would tell you. A z-score of -3 tells you that your score is below the mean, not that the mean is below your score. Wasn't intentionally trying to be tricky there, but it's important to get that. Approximately how many patients would have scores lower than an individual with a score of 1.96? So there you are in your map. You have your 0. You go to where the 1.96 is. Now the question is, how many patients would have scores lower than that 1.96? Would it be 97.5%, 97.5%, 98.04%, 2.5%, or we can't do this unless standard deviation. So you've got your map, you've got your 0, you've got your 1.96, or you can round it to 2. You say, what proportion would have lower? A. So we know that what proportion is between the +2 and -2? How much is?
95%.
95. That means how much is outside? 5. And that means you have 2.5 at each end, right?
Yes.
So to go all the way down, you got the 95, then you got to tack on that little 2.5. So 95 plus 2.5?
97.5.
Very good. Yeah. So Dean, you're with us. The standard score. What is it? Is it a mean score? Standard deviation of a particular score? A z-score or a constant? Yeah, a z-score is a standardized score. So it's not just a standard deviation of a score, it is a standardized score, and that's what a z-score is. Well done. I think there's one more. So you have the z-score of a patient. Their pocket depth is -2. That's the z-score for it. And then you have another patient, B, their z-score is 2.0. What percentage of people have pocket depths that are deeper than patient A, but more shallow than patient B? So you'd have to create your little map, right? You have patient A who's at -2, and then you're asking for deeper than patient A. Okay? Then you have patient B at 2.0, and you have more shallow than patient B. So which areas of the curve? Yeah, 5%. Very good. You guys are not easily cool. 5%. Any questions on that? You gotta draw it out. Either mentally kind of draw it out, or on paper kind of draw it out. Say where's patient A, where's patient B, where would deeper be for patient A, where would more shallow be for patient B? Yes?
Can you repeat that sentence one more time, sorry?
Yeah, sure. So you have a distribution of pocket scores. 2 patients, A and B. Patient A is down where their z-score is -2. Patient B is up at +2. So for patient A, you want what's deeper than patient A. So where would that be? To the left or to the right for patient A for deeper? To the right. Well, my right or your right?
All right. Wait, what?
Yeah. Shall we draw this out?
Yes.
Do you have markers?
There's one up there.
All right. All right, let's get a volunteer up there.
Catalina.
Catalina.
Social media.
AJ. AJ, just sit up there with me.
What does manliness have to do with volunteering?
Give us a big distribution. Nice, normal Gaussian. There we go. Can you see that?
Yeah.
All right. Show us where your middle is. Oh wow, it's very detailed. 60. Okay. All right. So patient A is at -2. So where would that be?
97 point something.
Okay. So show us where patient A would be on your map,
So
on
it's
your distribution.
And it's 97.7 something. So
you would think it's here, but it's negative, so you get it here, correct?
Actually, draw your 0 on there. Where's the z-score of 0? Perfect. Now, where's the z-score of -2? And that's where patient A is. Where's the z-score of 2.0?
2.
Yeah, show me where a
On the
z-score
right
of
side.
2.0 is on your map.
2.
In between 95 and.
Here.
Perfect. That's where patient B is. So we want pocket depths for patient A that are deeper than patient A. So shade the area that would be deeper than patient A. You're taking measurements where we're deeper than patient A be.
Left.
Okay? Okay?
Like in our mind, -2 is.
Okay. And then for patient B, more shallow than patient B.
Shallow?
The
So
other side.
here.
To the right.
And 2.
So it's 2.5 plus 2.5 is that.
So you got a lot more. Makes sense.
Okay?
So that's 1.5%.
So if that's 2.5% on the right that you
2.5.
shaded, and then 2.5% that you shaded on the left, you add those together, you get 5%. So you're gonna draw a map, and then anchor yourself in the map, start shading the areas that are of interest to you, and then it's easier to kind of say, oh, now I know what I want. But you are perfect in terms of saying where the 97.5 is, where the 60% is. You put the -2 correctly on the map, you put the +2 correctly on the map, and then it's just making sure you shade what you
So when
want.
you have a negative and it's 97 on the paper, you're not shading this side.
You don't shade anything yet until you know what you want. So right now you're just dropping where the landmarks are. So where 0 is, where -1 is, where -2 is, maybe -3 too. And you put where your 1 is, and where your 2 is, and your 3 if you need it. And then you say, okay, now what do I want? So we know what patient A is at -2 for z-score. So you say, okay, I've got -2. Patient B is at +2. Okay, I've got +2.
Okay.
And then you shade when you know which direction you want.
Say you're not asking a question.
Yeah.
And you find the z-score as -2.
Yeah.
You find the percentage here.
Yeah.
Where are you gonna shade here?
Okay, so in the table, and every book is different, in the table here, they said they shaded everything below the z-score. So in that table that you looked at, if you found a z-score of -2, and you looked in there and you found a proportion there, that proportion would be equivalent to everything to the left of it.
So am I shading here?
To the left.
That's the question. The question is, where would more shallow pockets be, or deeper pockets, and where would more shallow pockets be?
Without that question.
Where do you want to shade?
Yes. If you have -2 and 97.7, where, but it's a negative, where do you shade for that?
To the right.
Oh my.
To the right.
Like this? All
Oh,
this.
because it's negative, right?
Yeah, because it's negative, and you're saying, now, from here, give me 97.5%, take everything up.
But if they ask the question, you ignore the negative and you just answer their question. Thank you.
So either up from the negative, or go to the positive and down would give you 97.5%. You got it.
Makes sense.
Excellent. Good job. All right, so the last one, you guys have your,
Yes.
okay, so the last one is, which of the following does not apply to the normal distribution? Normal curve is unimodal.
That one.
Normal curve is symmetric about its standard deviation. Total area under the curve is 1. Mean, median, and mode are all equivalent to each other. Which of those four
A.
does not apply
A.
to the normal distribution? So is a normal curve unimodal? Yeah, I see some head nods. Yeah, it only has one mode.
Oh.
Yeah.
Oh, that's
So if it only has one mode, then let's go to the next one. Normal curve is symmetric about its standard deviation. Do you like that? Symmetric around, I've seen some head shakes. What would you rather it say for you to like it? Mean. It's symmetric about its mean, not the standard deviation.
That's me.
Yeah.
Okay.
So since it doesn't say it's symmetric about its mean, that's why we don't like it, and we say, yeah, this one does not apply to the normal distribution. The moment distribution is not symmetric about its distribution, it's symmetric about its mean.
So it's because I thought it has, that's a normal distribution, right?
Correct.
And I thought the two extremes make it bimodal.
No.
Okay.
No, the two extremes don't make it. Remember the definition of a mode. A mode is where the peak is. This only has one major peak. So it's unimodal. And that's a feature of the normal distribution. It's unimodal. Other questions?
Did you always want to do this career?
Is that a compliment or?
You know, I don't, you don't really hear about it. I didn't learn about this in undergrad, and so I'm just trying to figure out, like, how did you decide, oh, this is what I want to do in my life?
Well, yes, I always wanted to meet you guys. I knew some way, somehow, I got to figure out how to meet you guys. No, I didn't always know I wanted to meet you guys, but yes, I knew I always wanted to kind of work at the interface between statistics, not math, statistics, computers or informatics, information science, and healthcare. It was, I would say it was kind of providential how you got into it. I was a junior in high school. This is a while ago. This was in the very early days of medical informatics. And they had a summer program at our medical school at the University of Pittsburgh. And what they would do is they would recruit high school students and let them participate in research. And they had about 14 research areas that you could participate in. They were classic, diabetes, malaria, stroke, cancer. And then there was one on there that none of us knew what the heck they were talking about. It was called medical informatics. It was just like a match program. So you pick your top 3, you come back next week and they tell you where you matched and they tell you which lab to go to. Everyone else matched except for me. I got none of my top 3. And I'm sitting, this is how I knew I was interested in statistics. So wait a second. I counted out how many we were, and we started working through the top 3, and I started working through the number of options. Now, how is it possible that I didn't get any of my top 3, but these guys did? That just doesn't make statistical sense. So when I'm trying to work that out, they said, well, Udo, we're sorry, but would you be interested in getting involved in medical informatics? I said, I don't really have a choice, do I? Because that's all that's left. I can't pick anything else. So sure, let me do it. Had the best summer ever. Went to Carnegie Mellon University, and we were working on statistical algorithms to be used to help clinicians figure out what's the most likely diagnosis for a patient who's presenting with certain symptoms. So this is, I'm dating myself now, this is 1992. So this is way back that we were trying to do this. And that's how I got involved. So since then, I've taken more math classes, more stats classes, more computer science classes. And that's what brought me down from Oregon. Dentistry was, I had no clue about dentistry. I've been working over at the medical center in the radiology department, but we were consulting on some programs that you would have, and they had a statistician who resigned, dropped out. They asked if I would help out. I said, sure, I'll help you guys out. So that's why I'm actually here helping you guys out. It's fun. Nice to meet you guys. Do you guys have any questions before we split for next week?
Do I have a homework?
Do we have homework? No, there isn't a homework assignment. You have the midterm. You want homework on top of the midterm? Okay.
Easy.
Sunshine.
No. Sorry.
No. Definitely not. Alrighty. I guess you guys have some time before your next class.
25 minutes.
Midterm tomorrow
Wednesday, tomorrow, correct.
for Monday.
And it is due Monday.
Not on Friday.
It was due tomorrow. Tonight.
Oh no, it was due on the 2nd.
Nope. It was due today at 11:59.
Really? Oh,
So
I had no idea.
So I just
we match tomorrow.
Yeah.
Where were you at?